The photoelectric effect was one of the first quantum phenomena to be observed. Basically, what was observed was when light of a sufficiently high frequency was shone onto a polished zinc plate, the zinc plate discharged. This observation was turned into an experiment which looks pretty similar to this. And you're going to use this PhET application to collect data and use that data to come up with a value for Planck's constant. So this is how the application works. When you open it, you get this screen, and we can see several controls on it. We can see the intensity of the light, which I'm going to ask you to put up to 100%. You can see this next slider below it, which adjusts the frequency or wavelength of the light. And you can see a slider at the bottom, which adjusts the voltage of the battery down here. So I'm going to set the voltage of the battery initially at 0. It's a little tricky to set, but you can do it. Set the voltage to 0. Almost there. There we go. On the right, also, you have some selections that you can choose from. The target, that's this plate on the left that the light is shining onto, I want you to select zinc because that's the metal that was used in the original experiment. And you can see when I select to zinc, all those electrons that were being emitted by the plate have gone away. And if you start sliding the wavelength or frequency slider around, you'll see that in actual fact there are no electrons until you get to a certain frequency, a certain threshold frequency. So I've brought it down to a wavelength of about 270 nanometers, something like that, firmly in the ultraviolet range. And now you can see the electrons are being emitted, and some are being emitted faster than others, and they're traveling across this empty space. This is a vacuum in here, and they're reaching the other side. And because the electrons are traveling from left to right, we're getting a current. Now it's possible, by applying a potential difference across the plates in the opposite direction, to slow those electrons down and reduce the current to 0. You can see that if I move the slider very slightly to the left, my current, my very small current of 16 milliamps, can be brought to 0 with a potential of only negative 0.2, I think. Let me just slide that over. As you can see, it is slightly tricky to adjust this slider. I think with a mouse you can do it. There, negative 0.2. If I move it all the way over to the left, it still remains 0, but it's way too much. The field is way too great. You can see the electrons can barely get out of the plate now. They're just trying to get out, but the field is so great, they're being pulled back in. So for this, if I slide it over just to 0.2, that is enough to bring the current down to 0. So what I'm going to ask you to do in this virtual lab is to collect pairs of data for the frequency of the light used and the voltage required to bring the current to 0. So the lowest voltage required to bring the current to 0. So here we are, again, 268 nanometers, so I'll record that wavelength, and negative 0.2 volts, I'll record that potential that's required to bring the electrons to a halt. You're going to collect 7 pairs of data. Just to show you how this works, I'm going to select another wavelength, a much shorter wavelength, higher frequency. You can see that a lot more electrons are being emitted, and I'm going to have to increase the potential negatively to bring the current down to 0. So I just want the minimum voltage required to bring that current to 0. There it is, there, minus 3.4. Okay, so you're going to collect pairs of data for wavelength and voltage between the highest value you can get, which is about 270 nanometers, and anywhere all the way down to the bottom here. Once you've collected that data, you're going to plot a graph of voltage on the y-axis, and you're going to plot frequency. So you'll have to work that out, and frequency on the x-axis. And then from that graph, you will be able to determine a value for Planck's constant from its slope.